All right, good morning. We have some things to clean up. I want to start off by talking about the chain rule. We just use the chain rule without a proof. We will prove the chain rule to close that up. We've proven everything except for the chain rule, really. So we're going to do that. And then we're going to go back to doing some implicit function stuff and maybe do some related rates. Yes.
Is our implicit function going to be on the test?
No. So, yeah, again, we've broken up the test on chapter 2 into two pieces. So the first part is going to end at the chain rule, which is due tonight. No, tomorrow night. Tomorrow night, yeah. So while we're talking about the chain rule, let's go ahead and prove it. So we have made the claim that if h of x is equal to f of g of x, then h is a bad letter, as I'm about to. Let's do c for composition. If c of x is equal to f of g of x, then the derivative of c is f prime of g times g prime of x. All right, so you were using this a lot in the homework last night. This theorem we'll be using a lot at the end of test 1. Here's the proof of that. C prime of x is equal to, we're going to use a little bit of math magic here. It's the limit as h tends to 0 of c of x plus h minus c of x all over h. Now let me think for a moment whether it's not going to really matter to do it this way or using the other definition. Okay, this is fine. So this is equal to the limit as h tends to 0 of f of g of x plus h minus f of g of x all over h. Right. So all you're doing is plugging x plus h in for x. This is equal to the limit as h tends to 0 of f of g of x plus h minus f of g of x all over h and then now I'm going to introduce something else, and it's going to be g of x plus h minus g of x all over g of x plus h minus g of x. I'm going to introduce that now. So I've introduced that new term, and that because that's going to help us out tremendously. This is equal to the limit as h tends to 0 of f of g of x plus h minus f of g of x. And then what I'm going to do now is I'm going to switch the h and this. I'm going to switch denominators. This is g of x plus h minus g of x. And then this is g of x plus h minus g of x all over h. And so I'll make that comment somewhere that here I'm just switching denominators. Right, so I'll switch. I can do that because we are just multiplying the denominators. It doesn't matter the order. The other remark we need to make, I need another color. A beautiful color. Is that this now looks like f of t. This is like f of x. This is all over t minus x. I hope we know where that goes. Right, so now in evaluating the limit, what is this? Can someone see what this is as h goes to 0?
The limit as t goes to x of f of x 2.
Something like that. Can you see what that? Well, do we know where this goes? Where does that go to as h goes to 0? What's the limit of this as h goes to 0? That is g prime of x. For sure. What is this? Do we see that this is a derivative of f? F prime of what? It is. It is. And that's the end of it. Right. So as h goes to 0, this goes to, it's like you're doing f of t minus f of x over t minus x, which is just the derivative of f at x. But in this case, x is not x, it's g of x. Right. So that is the chain rule. Okay. Questions from the please?
Can you explain again how you got f prime g of x?
Yeah, so that is, thank you, because that is not a trivial remark. So the limit as u tends to v of f of u minus f of v all over u minus v, what is that? What is that? The derivative where? At v, excellent. That is f prime of v. Okay? That's the definition, one of the two definitions. Now, I don't want us to be intimidated by notation. When I write the limit as h tends to 0 of f of g of x plus h minus f of g of x all over g of x plus h minus g of x, I want us to recognize that as h goes to 0, g of x plus h goes to g of x plus h goes to g of x, right? So as this is a beautiful color. As h goes to 0, g of x plus h tends to g of x, right? And so this is like u going to v, right? So this is like u, and that's like v. This is like u, and this is like v. Right? So as h goes to 0, g of x plus h goes to g of x. So it's like you're just substituting. There's u, that's v. And so this is just f prime of g of x. That's the point. And we knew this is kind of an argument that we had to make because f is inside of g, and g depends upon x, and x is moving, right? So this is exactly what happens with composition. You got something inside something else, and everything's moving, right? And so This is all we mean, that f depends on g. Right? Questions on that? Does that answer your question?
Yeah.
No. Okay. Other questions about this? Thank you. Again, just being technical and tying up loose ends. Okay. So there's the chain rule. Again, someone asked a question about the homework. There are two things about the homework I want to talk about. One is that Jessica definitely wants to do a chain rule problem like this. F of x is equal to x squared times g of x. And I'm going to tell you that g of 1 is 5 and g prime of 1 is 3. I'm sorry, of 1 is 3. The question is, what is f prime of 1? Or that's 1. And that you don't need the chain rule on. And so, but if we have h of x is equal to, let's do something like, say it again. Yeah, so we can do f of g of x. I'm going to tell you that g prime of 1 is 7. F prime of f prime of 2 is 12. I'm going to tell you that g of 1 is 3, and that f prime of 3 is 15. The question is, what is h prime of 1? Today? Oh yeah, absolutely. And I can see why she likes these, because, you know, in order to do this, you need to know the formula for the chain rule for sure, right? At least for the second one. The first one, you need to know the formula for the product rule. I'm sure I'm going to write a product rule problem, and she's going to add something like this probably, right? So this is U, that's V. I should have used this thickness a long time ago. This is way better. F prime of X is U prime V plus V prime U. U prime is 2X. V is G of X. V prime is G prime. And then U is X squared. And I think we have all of those values. And therefore, f prime of 1 is you put a 1 everywhere there's an x. It's 2 times 1 times g of 1 plus g prime of 1 times 1 squared, all of which we know. $13. Two times 5 plus 3 times 1. H prime of x. Say it again. Is equal to f prime of g of x times g prime of x. H prime of 1, therefore, is equal to f prime of g of 1 times g prime of 1. Again, I think we have all these values. This is f prime of g of 1 is 3. times g prime of 1 is 7. F prime of 3 is 15 times 7, 105. So what was the issue with these? Yeah, Victoria, what was the issue with these?
I don't know, it was just like hard to follow at first.
Oh, okay.
Like going through it.
Okay. Yeah, and again, you can go back through the homework and just do them again and practice. But I'll gauge in a battle with Jessica about this. So, but you should be ready for it just in case. Questions about this? Yes, please.
So the F prime is just
I didn't hear you.
the F prime is
Yep. It wasn't necessary here. Yeah. Again, don't be intimidated by the story, right? So what's good about understanding the concept is that it doesn't matter how I tell the story, you're going to understand what you need to do, right? Show that h is increasing at 1, right? Same thing, right? If I say, suppose h is the composition of two functions f and g for which this is true right here, show that h is increasing at 1 and how fast is it increasing at 1? Right? I'm asking you to do exactly the same thing here. Okay. Questions on that formulation? No matter how I tell the story, and I intend to tell the story in all sorts of ways, right? So the bottom line is I'm probably asking you to take a derivative, right? I'm probably going to have to just be asking that no matter what the story is. The other remark I wanted to make about the homework was this funky natural log thing, right? So logarithmic differentiation. So I think you were given something like y equals the natural log of the square root of some ridiculous thing, right? Yeah, 2x plus 3. Oh, it doesn't matter what it is. 7x minus 5, right? You want to find the derivative. And so we have some log rules, right? And it's good to use them here. So we know that, recall that the log of a times b is equal to the natural log of a plus the natural log of b, right? Remember that? Why is this true? You're adding exponents, nicely said. That the power of a product, what do you do with the powers of a product? You add them, right? So the power of a product is the sum of the powers. That is excellent. The log is the power. And so here we're subtraction. And the power of a power, what do you do with the powers?
Put it in front of the element.
But what do you do with the power of a power? You multiply. Right? So the power of a base, you simply multiply the powers. Right? All of these things should be helpful for us in this particular case because we can do a ton of simplification first. The natural log of the square root of 2x plus 3 over 7x minus 5 is equal to the natural log of 2x plus 3 over 7x minus 5 all to the 1/2 power. This is equal to, and notice we aren't doing any derivatives yet. This is all simplifying. This is equal to, we can label, this is rule 1, rule 2, and rule 3. By rule 3, I can bring the power in front, having this be a, and the power being 1/2. This is 1/2 the natural log of 2x plus 3 over 7x minus 5. This is equal to, I'm currently dividing by rule 2, the difference of those. This is equal to 1/2 the natural log of 2x plus 3 minus 1/2 the natural log of 7x minus 5. And now we're prepared to take a derivative of this. Did I call this something? Was this f? I don't think I called it y, x. That's y, and that's a y that I like. I prefer this one, right? So then the derivative is easy. We'll recall as well that the derivative of the natural log of u is 1 over u times the derivative of u. And therefore, y prime is equal to, I'll hold the 1/2. The derivative of the natural log of 2x plus 3 is 1 over 2x plus 3 times the derivative of 2x plus 3, 2. Minus, I'll hold the 1/2 as a constant on the outside. The derivative of the natural log of the natural log of 7x minus 5 is 1 over 7x minus 5 times 7. Questions? So by using those rules, taking derivatives of logs is really, really straightforward. Yeah, go ahead.
On the test, do you want us to do it like that question comes up like this, or should we do it the actual way we learned it in class? Because originally when I did this question, I had 3 different sections of derivatives because it was like a consistent chain rule.
Yeah, no, that's why. Yeah, this is way better. Yeah, no. I mean, so mathematicians, almost to a fault, we love beautiful proofs, right? And so beautiful work is efficient, it's clean, it's concise. You're right. So nobody wants to do 1 over the square root of 2x plus 3 over 7x minus 5 times the derivative of the square root of 2x plus 3 over 7x minus 5, which means that you need to take the derivative of the square root of 2x plus 3 over 7x minus 5, which is a power rule, and then inside of that there's a quotient rule, and then that's just all crazy. Nobody wants to do that. So that's why this is much more preferable. Okay. Questions about this? Okay, while we're here, using log powers now, we can actually find the derivative of this thing. Now we'll see if this even shows up. We'll come back to that, but y equals x to the x. That thing's ridiculous. So that thing's going to increase and increase and increase. Of course, that is going to be, this is a function, we talked about exponential functions. In terms of the most applicable functions we talk about and the way they increase, the exponential function is the most powerful. But of course, you can get as sick as you want, right? X to the x, of course, increases faster than e to the x because e is constant and x is not, right? So that we're talking about 10 to the 10. At 10, it's already 10 to the 10th, right? So at 10, it's already 1 with 10 zeros behind it, right? So it goes super crazy.
How come there aren't any negative values?
That's a great question, right? Why is that? Why is that? Why would a programmer have an issue with the x-axis, the negative x-axis here? Plug in some values. What's the issue? Plug in some negative values of x. What issues will we run into? What is it at negative 1? What's negative 1 to the negative 1?
Negative 1.
Negative 1, right? What about negative 2? Say it again. Negative. Is it positive or negative? Positive. Okay. So that seems to be okay. Negative 3. negative 1 over 27. So it seems like it's bouncing up and down, right? Okay. So those numbers seem fine. Are there any problem numbers? What about negative 1/2? Then you're taking the square root of a negative number, right? So let's put that in. So if you put in negative 1/2, so if I call this f of x, right? F of 1/2, or negative 1/2, is negative 1/2 to the negative 1/2. And so that's 1 over the square root of negative 1/2, which is not a real number. So it's not defined at negative fractions, right? It's not defined at negative fractions. Now, it seems like it's pretty easy to prove that it's defined at every negative integer, right? But that certainly means, what about this function on the x-axis? What is it that we know? That it's certainly not continuous. It is not differentiable, therefore, and so the programmer, just gives up. This thing looks super crazy. It's only defined on the integers, basically. So the general point is that you're never going to get a programmer to be able to program something in which the powers can be decimals and the base can be negative numbers, right? Because whenever you have a decimal as a fraction, whenever you have a decimal as the power, then you're talking about taking roots, right? And if you're talking about taking roots, then that means you're talking about you need to avoid negative numbers. And so, you're just not going to see anything over here in terms of connecting dots. Is that okay? Did that answer your question? Okay. Yes.
Can I ask an unrelated question?
Go ahead.
What's 0 to the 0th power?
That's a great question. So what is 0 to the 0? Right. So that's not so unrelated, right? So 0 to the 0 power is, right? So that is that's up for debate. One would say that it seems like whatever it is, maybe it's the limit as x tends to 0 from the right of x to the x. Maybe that's what it should be, right? And if we define it to be that, then it looks like it should be what? 1. Right. Now in Calc 2, we define it to be 1. We define it to be 1. But in general, we're going to have all sorts of limits where you get 0 to the 0 and it's not 1. So it just depends. It's indeterminate. So this looks like 1. All right. But let's go ahead and find this derivative. If y is equal to x to the x, what is y prime? And here is where we use the natural log. And here's where it should be clear that you should use the natural log. Why? Because we're interested in x, and x is both in the base and the exponent, and this is problematic, right? And so in order to relieve this issue, we'll notice that the natural log of y is equal to the natural log of x to the x. I guess you could change the base. I don't think I want x to be the...
Would you line x over line x?
Say it again?
I'm not sure, but you could change the base.
And what base would you use instead?
You could do natural log over line x.
Oh, I think we're probably doing that. Yes. Yes. Okay. I've never thought about it that way, but yes, we are. Yes. Okay. That's interesting. Okay. Wow. That's interesting. So natural log of y equals the natural log of x to the x, and then the natural log of y is X, the natural log of x. Right, so again, this is by the power rule. Right, so recall that all I'm doing is bringing the power in front. The natural log of a to the p is p, the natural log of a. So I just bring the power in front. And now we'll take a derivative. So that the derivative of the natural log of y is equal to the derivative of x, the natural log of x. We know y is a function of x. So the derivative of the natural log of y is 1 over y times the derivative of y. What's the derivative of this? What do you have to do? That's the product rule. This is u, that's v, u prime is 1, v prime is the derivative of the natural log of x is 1 over x. U prime v plus v prime u gives us 1 times the natural log of x plus 1 over x times x. 1 over y times y prime equals the natural log of x plus 1. Ooh, I feel like I'm going too fast. I'm solving for y prime. I almost have it. I'm going to multiply both sides by y, and we'll have it. Y prime equals y times the natural log of x plus 1. But then what was y again? Y was x to the x. That's x to the x times the natural log of x plus 1. That is the derivative. So, I'm sorry, go ahead.
On the last slide, when you were giving the derivative of y, you did 1 over y and
Yeah.
you didn't do it over the other side.
That's correct. That's right. So, thank you. So, I just really like this purple color. I don't want to change to any other color, but let me try. Let's try this green. Okay, so we're talking about the derivative of the natural log of y versus the derivative of the natural log of x. Okay, so we had, that lasted long. We had said that y is a function of x, right? So y depends on x. And so here it is the chain rule. And here you can use the chain rule as well, right? So the derivative of the natural log of x is 1 over x times the derivative of x, which is, what's the derivative of x? 1. And so it's just 1 over x. So we're always using the chain rule. It's just that when it's just x inside, you're not doing anything. Is that okay? Yeah, so that's the difference. But when it's any other function other than x, then it's 1 over y times the derivative of y. Right? So whenever y is more complicated than just x. That is, of course, crucial for the problems that we are about to do that are implicit. Okay. So the point of this last problem is just to notice that when you have issues with powers of powers, then it's probably good to introduce the log, right? And then when you're taking derivatives with log functions involved, think about those rules to make it simpler before you start taking derivatives, right? So remember the log rules. And again, this is exactly why we talked about this in pre-calculus, right? These log rules for these particular problems. Yeah.
I think we answered this before. When we're writing our test, how far from Mississippi is it? Just like within a certain boundary?
Well, this is almost an impossible question. So because because the question is this going to be enough, right? I will alert Jessica. Jessica will be giving the test on Friday. If you're unsure, just ask her, is this enough, right? And I'll let her know that that you might be asking that. And this happens in every class, particularly during the first test, right? You get the first test in somebody's class, you never had them before, you don't know how the grading is going to be, right? So all of these are reasonable questions, and I hope that after this first one, you get an idea of what we're asking for. Yeah, thank you. Yes, go ahead.
Like for y equals x to the x, like you asked what is y, but we ended in y side, so.
Let's take a look. So yeah, I was just wondering. I just wanted to replace. So y was x to the x, right? So we were given something in terms of x only. So I hesitate to write this as the answer because it is not back in terms of x only. And so I just wanted to say, well, wait, I need to get rid of this and write this in terms of x. And then I just go back and say, well, wait, y was x to the x. And so I just replaced it. Right? Y is x to the x. So when I did all of this and I got this y here, I just wanted to get rid of it and write it back in terms of the x that it was. Right. I don't know if that answers your question. You were asking...
Like, is the question what is y prime? Or what is
yes, the question was what's the derivative? I'm sorry. Oh, I'm sorry. I apologize.
Okay.
Yes. What is y prime? Thank you. Yeah. Other questions about this? Good. Okay. So going back to this, we had left off yesterday talking about something that was slightly implicit. X squared plus y squared equals 1, right? And we were asking, what is the derivative at the square root of 2 over 2 minus the square root of 2 over 2. What is the slope of the tangent line? Is the graph going up or down at this point? And so forth. We can ask all sorts of things. So that graph again is here. I will highlight this one. Instead, let me just go back home. Okay. So we're asking about that. We're asking about that thing. And again, from the context, I don't know why it won't let me. Oh, maybe it's that. Okay, here we go. Okay. We're asking about the slope here, and we want to find this equation. So square root of something like that, right? And so here, y is implicitly a function of x. Y is some function of x, right? Now we could explicitly, as Diego mentioned to me yesterday, we could of course explicitly solve for y, right? We know that y squared equals 1 minus x squared, right? And that y is equal to what?
Square root of 1 minus x.
No, it's plus or minus the square root of 1 minus x squared, right? And so here, this immediately tells us exactly what we can see from the graph of this, that y is not a function, right? Because you have to decide which one it is. But from the context of this problem, it's clear that I'm only interested in the... Which one, the plus or the minus?
Plus. Positive.
Why? Why am I interested in the positive?
Because we're looking for a positive derivative, the positive slope, tangent line.
Oh no, but that's right. But I care for the moment. This is about y and not derivative. Why? Which one do I want for y? Positive or negative?
Increasing.
No, you're talking about the derivative again. What do I want for the function y? Do I want the positive y value or the negative y value? How do you know? Because I want to know at this point at the negative square root of 2 over 2. Right? So this would be the function I would be interested in. Right? And so what that means is when you look at this graph, again, this is exactly what the implicit function theorem says. It says that, you have something that's not a function, but I actually just want to pay attention to this part only. And then that's okay. It's okay to do that, right? If I just ignore the top, right? So it's like just locally, again, I've been doing this, just in this box, it's all good, right? So it's just focusing on that area. Okay. But as we already mentioned with the whole natural log stuff, I really don't want to do this, right? I don't want to take a derivative of this. It requires the chain rule. And I mean, of course, you would be able to get the same answer. The hope is that whatever we're about to do implicitly, that we'll be able to get the answer the same way, right? The same answer. Okay. That in addition to the fact that I'm going to give you some that you can't solve for y, right? That you just can't do it. So not only should this be somewhat easier than just doing this explicitly, but then sometimes you just won't be able to find the explicit expression. Okay, so let's go through the procedure. It's x squared plus y squared is equal to 1. And we've done this so many times in other contexts, but we are going to take a derivative and use the chain rule. Again, y is assumed to be a function of x. So that means that the derivative of x squared plus the derivative of y squared needs to be equal to the derivative of 1. The derivative of x squared is 2x. The derivative of y squared is
The derivative of y squared.
2 times y times the derivative of y. And that equals the derivative of 1. The derivative of 1 is 0. And it is y prime that we're looking for. Please.
Why is it 2 y times y? Because I never understood that when I was doing this question.
Excellent, excellent. So it's all based on this assumption, right? So what I want to do is, thank you for your question, I want to take a derivative. So suppose y is equal to the sine of x, right? So what's the derivative of sine of x squared? 2 sine x cosine x. What you just did was you took 2y times y prime. 2y times y prime. Now it just so happens that I don't know what y is. But I know it's some function of x. And if it's any function of x, then I need to do 2 times y times its derivative. Is that okay? Yeah. So yeah, a lot of people have that issue that, well, wait, where did this y prime come? And it's because if y is any other function that's more complicated than x, then you have to multiply by the derivative. Is that okay?
Yes.
Yes. Question here?
Oh yeah. Can we write dy dx instead of y?
You can. Yeah. Of course, Leibniz, of course, is a genius, but I never use his notation. So some people like to use 2x. To each person their own. Right? Yeah. Some people like to do that. I have no idea why, but yeah. we can do that. I'm looking for the rate at which y changes with respect to x, right? That's the notation for that, the rate at which y changes with respect to x. This is notation we'll definitely be using in Calc 3, so the notation is very useful because in Calc 3, you know, we've been so biased that we think that y depends upon one thing. What happens when y depends upon three things, right? What happens when y is a function of x, t, q, m? Then we can ask, well, how does y change when x changes? Or how does y change when t changes? Or how does y change when w changes, right? When y depends on more than one variable, then you can ask how that one thing changes when you leave all the other variables constant and then you move one of them, right? So then when you ask about that, that's still a derivative question, but then you have to say, well, how does y change with respect to x? Or how does y change with respect to z? And in that case, y prime is such terrible notation, because then you don't know which variable's moving, right? And so that's when Leibniz notation is really useful. But now when I'm doing this, you know, I know that when I say y prime, then x is the only variable, it's the only thing that's moving, and I know everything's with respect to x, right? So this notation is to say I want to know how fast y is changing when x changes, and I'm being lazy. I don't have to do that because x is the only thing that's changing, right? Okay, so now, when you do this, it becomes an algebra problem. We're literally just solving for this. We're going to get this by itself. And so I have 2x plus 2y times y prime is equal to 0. And so I'm going to subtract 2x on both sides. 2y times y prime is equal to negative 2x. And then y prime is equal to negative 2x over 2y. And that means that y prime is negative x over y. Now, I had just done the derivative of x to the x, which at the end of that problem, I got something similar to something like this in the sense that I got y prime in terms of x and y, and then I went back and I put the y value, I put what y was, right? Y was x to the x, and I just put that back in. And I got this beautiful formula for the derivative in terms of x only. We have no chance here to do that, okay? So now, and for the problems I give you, you will not have a chance to figure out what y is. And so this would just be the answer if I was just asking for the derivative, right? But I wanted to know at a specific point, it was the point the square root of 2 over 2 comma minus the square root of 2 over 2. And now we just plug that in. Okay. So that y prime is equal to minus the square root of 2 over 2 over negative square root of 2 over 2. And that is 1. The slope is 1. Let's go ahead and write the equation of the tangent line and graph it. So now we have the slope. So the tangent line, y minus f of a equals m times, I'm sorry, we know m, it's f prime of a times x minus a. That gives us y minus a funky square root of 2 over 2, and it's plus equals 1 times x minus the square root of 2 over 2. Y plus the square root of 2 over 2 equals x minus the square root of 2 over 2. Y equals x minus the square root of 2. We'll graph that. And that should be tangent. Let's see here. Y equals x minus the square root of 2. Go ahead.
Like for the test, is it fine if you write y equals minus square root 2 over 2 minus square root 2 over 2.
This here?
Yeah.
Yeah, that's great.
And then like add the square root 2 over 2.
I'm sorry, do what?
Like if your point has different x and y values,
Yeah.
is it fine like if we just
If you just, how? What do you mean?
like,
If you,
like I write it in f prime a times x minus a plus f of a, like in that form.
you write it, say that again, you write it as what?
F prime a times x minus a plus f of a.
Oh, that's fine, of course, yeah. Okay, that's okay, weirdo. Right, question?
Same one.
Same one? Okay, excellent, okay, good. Yeah.
Can I ask another like different?
Go ahead.
Is there a way to like reverse the derivative so you get the function back?
That's a great question. So yes, so you're good at that. So at this point, there's really no reason to do that, but you could. I mean, you certainly could do that. So if I give you the derivative, the question is, what's the original function? I guess that happens a lot, right? Sometimes you're given the velocity, you want to know the position. So we're heading in that direction. We're going to be doing that. I have to give a reason why we would do that. What's useful about that, right? But yeah, we're going to do that for sure. Other questions about this? Let's do some more funky ones. The problem is that we'll need to find a point on this on the curve, but let's play with some. So x squared y minus, oh actually we had some, right? Minus, let's do 3x y plus 1 equals 0. Let's do plus 2. Oh, I'm sorry, let's make this x to the third. And then at the point 1, 1. I have no clue what this looks like. Near the point 1, 1, is the graph going up or down? Oh, okay. I have no idea. Yeah, I have no clue. So, good. So the claim is that it's going up. Okay, no, I have no idea what this graph looks like. So no, this is why this is good stuff, because we can answer that question without knowing what the graph looks like, right? So, of course, this whole story is just like, well, what's y prime, right? And so we're going to take a derivative, and then we're going to get y prime by itself. Now, we should notice that y appears twice, right? So y appears here, right? It appears here, and it also appears here. And so if we take a derivative, how many y prime should we expect? 2, right? And so we're going to just go ahead and have to solve for them, right? So we'll take a derivative. So step 1 is take a derivative. So here I'm going to go into teacher mode and do this methodically. Accuracy. I want it to be accurate. I want to be right. Okay, so first I'll need a derivative of x squared y to the third. What rule? Product rule. I'm clearly multiplying two things. This is u, that's v. U prime is 2x. V prime is, what's the derivative of y to the third?
3y squared times y prime.
3y squared times y prime. Questions on that? U prime v plus v prime u turns out to be, u prime is 2x times v is y to the third plus v prime. Where's v prime? There it is, 3y squared times y prime times u, which is x squared. So this first derivative is 2xy cubed plus 3x squared y prime. The derivative of this we've now done. And again, if you do it, you practice enough of these, and I'm sure Jessica will make sure that happens, that we'll be able to do all of this in one line. Right? The derivative of minus 3xy is also the product rule. U, V, U prime, negative 3, V prime is
y times y times.
this is y prime. The derivative of y is 1 times y prime. UV minus U prime V minus V prime U. U prime V minus, I'm sorry, plus V prime times U negative 3y minus 3y prime. Where's the x? U prime V, so this is an x, right? All right, so that's an x. Questions? Go ahead.
Like you can also factor out the negative 3 and then just call x u and y v.
Say that again?
Like you can factor out the negative 3 and then call x u and then y v.
Yep, that's right. Okay. All right, I think we are ready. The derivative of 2? 0. So then then the derivative becomes, once we have done all this derivative stuff, we're talking about 2xy cubed plus 3x squared y prime minus 3y, there's a y prime here, right? 3y minus 3x y prime is equal to 0. Right. So yeah, so this is style. I tend to compartmentalize my derivatives and then bring them all back, and then now it's an algebra problem. You're going to get y prime by itself. When you do this first derivative step, you'll get a whole line like this in terms of y prime, and then y prime, it'll be a linear function of y prime, meaning that in order to get y prime, you will do the same thing every single time. If it's not involving y prime, move everything else to the right-hand side or the other side of the equal sign, and then you can factor out y prime and then divide. That happens every single time at this step. So we'll move non-y prime terms to the other side. (3x squared y prime minus 3x y prime equals negative 2xy cubed plus 3y. And then we will factor out of y prime. This is y prime times 3x squared y minus, is that 3x? And that equals minus 2xy cubed plus 3y. And so y prime is equal to minus 2xy cubed plus 3y all over 3x squared y minus 3x. Looks like we're going to have some problems at 1, 1. Go ahead.
3x squared y squared.
Yeah.
Is it? No, drop it. Thank you. at 1, 1, y prime is undefined. Plugging in 1 into the numerator and denominator, you get 3 minus 3 on the denominator. You don't get 0 in the numerator. X squared y cubed minus 3xy. X squared y cubed minus 3xy plus 2 equals 0. Whew, my goodness. One, 1. X equals 1. Right. Tangent line looks vertical. Questions on that? Undefined. Right. Super funky. Right. So that for these types of problems, it's almost the hardest thing to do is to 1, negative 2 is on the point. Let's find that slope. Right. So what's nice is that even so, it's harder to find points on the graph than it is to actually find a formula for the derivative, right? Right. But it looks like 1, negative 2 is on the graph. Let's verify that. Is 1, negative 2 on this graph? 1, negative 2. That's negative 8. 1, negative 2. Plus 6. Plus 2. That is 0. So 1, negative 2 is on this graph. What's the slope? So super careful. Again, Jessica and I got into a battle over who was going to grade the test. She's just way too nice, isn't she? She's just crazy. I said, no, Jessica, I'll grade it. She said, oh, no, I'll grade it. I said, no, I will grade the test. She said, well, you're going to be out of town. I'm going to collect these on Friday. I'll decide whether I'll grade it, and if not, I'll leave it to you. I said, great. I'm so happy I work for you. Yeah. But somebody's going to grade it. And so I bring this up only because, tons of minus signs here. Don't miss any. Don't miss any. Because I think that if you miss minus signs and she's grading, you're going to get wrecked. So, yeah. So don't miss any. I just said she was so nice, didn't I? But, yeah, just be careful. Go ahead.
Oh, I just have a question. Is she volunteering for this?
No, she gets paid.
Did she seek it out? Was there an advertisement that she was how does one come into this?
Oh, that's a great question. Okay, that's what you're asking. Okay. No, so okay. Are you trying to take her job? That's okay. You can have her job in a few years, because in a few years I'll be gone. She'll be doing it, and then she'll need some help for sure. That's right. No. So yeah, Ty. So Ty had a job opening, right? And so most people here in this place go off and do stuff over the summer, and so I've been doing this, for on and off for about a decade or so. So, she said, you can have a TA, and I knew Jessica already. So I was just like, I want Jessica. And you can see why, right? Yeah, she's great. So yeah, I recommended her, and Ty wanted. Ty didn't care who I picked as long as it was a reasonable person. Yeah. Yeah. But yeah, so she'll be finishing up next year at Nebraska. She's gonna be Dr. Jessica De Silva. Dr. Jessica De Silva, PhD in mathematics. Yeah. So yeah, so she's trying to bump me out now. So if you see me dead in the river somewhere, right? All over $5,000, by the way. That's right. So this is equal to minus 2 times minus 8 minus 6 all over. Looks like this thing's going to be positive, right? Which is what the graph indicates. Is that 12?
12 minus
3, yeah. 10 over 9. Y minus negative 2 equals 10 over 9 times x minus 1. Right? That should be the equation of the tangent line. Let's see if that comes up. Now, this could be wrong. I mean, this would be a miracle if we navigated this whole thing without making one minus sign error. Y plus 2 equals 10 over 9 times x minus 1. Y plus 2. Over 9 times x minus 1. Oh, it's beautiful. Beautiful. All right. Tangent line. Okay. So, of course, this already dispels the myth that the tangent line only has to hit the curve one time. That's nonsense, right? We only care about locally, that locally the tangent line looks like the graph, or the graph looks like the tangent line. Questions on that?
Ask another.
Go ahead.
Why something to the 0th power of 1?
Right, so that, we'll just knock that out. That's 1, except for 0, right? So we'll, for the moment, we'll leave 0 out of it because of the conversation we had earlier. Why is that? So this is good. So as I mentioned, I was doing professional development for teachers in Pittsburgh public schools, right? And we were talking about making our classes as inclusive and equitable as possible for all people in there. And one of the things that I was making the argument was that in order to be an effective teacher, then we need to have good relationships, right? So there's math, there is the teacher, there is the student, right? And all these relationships have to be good relationships in order to have a good, equitable environment. And so what I found out, and oh my God, I love those teachers, but there were some problems on this side of the triangle, right? That they were having issues with, like, some of them didn't like math. Some of them didn't like it, and some of them didn't know this, right, and why that was true. And so, you know, we had a great discussion as with me as a PhD in mathematical sciences, and them seeing themselves and identifying themselves as teachers first, and not so much as, you know, so they thought of themselves as math teachers, as opposed to being a math teacher, right? Where it was the teaching that was at the center. And so, of course, we should be striving to be a math teacher where you're doing both of these things, right? So they didn't know why this was true either, right? And so that was shocking to me and Michael Young, who was also running the professional development. So let's go ahead and end this now. So x, tell me about x to the minus 2. What is that? 1 over x squared. Great. What do you do when you multiply powers? What do you do with the powers? Add. Great. So x to the 0, right, is x squared times x to the minus 2. Is that okay?
Yeah.
That's x squared times 1 over x squared. What's that? Oh, okay. All right. So, of course, it has nothing to do with 2. That's any power, right? My question to you is this. So I did this with the teachers, and I said, could you show this to your class? Could I show this to you? Could I show this to you in the 8th grade? And you get it? Of course, I'm speaking to the best, right? But I asked them this, and they were like, maybe I could show this, right? So, yeah, it was just very weird. I appreciate your question. Does that answer your question? Okay, excellent. Okay, great. So let's drill in a couple more, and then we'll be done. So now I'm just going to throw up some crazy ones, right? So I have no idea what these look like. I would struggle to find a point on the curve where the derivative would exist. Let's do something like, let's do 4x e to the y equals, it's over 12. I have no idea what that looks like. I would be stunned if Desmos would be able to give me a graph of that. X squared y. The question is, find an expression for y prime. It's going to involve both x and y. X squared y to the third. Is it minus? What did I write?
Yeah, minus 4 x e to the y.
Equals
12.
Okay, that's not bad. Anything on here that's reasonable? What is that? No. Okay. We can find the derivative there. What's this? Is that a nice number? Oh, at negative 3, 0. What's the slope there? Negative 3, 0. So find the slope, find the equation of the tangent line to the curve there. That's pretty nice. So again, before we had all this nice software, again, we would have numerical analysts looking for points on this graph. Right? It's not even clear to me how they're able to even graph this thing, right? They probably let, x be constant and then try and find y and then do that. They have some algorithm to do this. So it looks like 3 zeros on the graph. Oh, it's negative 3, 0, right? Negative 3, 0. I'll follow those steps, take the derivative. They both require a product rule. We need to see 2 y primes. We'll solve for it. Yeah, and I think we'll be good then. Again, we are going fast. We're going fast. And so we're almost done with chapter 2. We're going to, we got to do some optimization. We're going to do some related rates. We're going to do some optimization. That stuff is fun, right? No? Here we go. Baggage. All right, pay for your own state. What was not fun about it? You can't even, okay, so wait, you only remember how bad it felt. That's right. Is your mind open to a different experience this time?
But it's probably because I was first learning it.
Yes. Okay, yeah. No one said the first time had to be the best, right? We need to take a derivative. Don't let me catch up to you. We need the derivative of x squared, y to the cubed, y to the third, y to the cubed, y to the third. I'm going to take a derivative of that. That requires a product rule, u prime v plus v prime u. Again, if you're a speed demon, go ahead and write all of this in one line. U prime 2x, v y to the third plus v prime is This looks familiar. 3y squared times y prime times u is x squared. This first derivative is 2xy cubed plus 3x squared y squared times y prime. I now need the derivative of 4x e to the y. I usually incorporate the minus sign. Of course, that u prime v plus v prime u prime negative 4 times v plus v prime is e to the y times y prime times negative 4x. Yeah. Minus 4e to the y minus 4x e to the y times y prime. I was adding these, right? Yeah, and that equals the derivative of 12 is nothing. So we've got 2xy cubed plus 3x squared y squared times y prime minus 4e to the y minus 4x e to the y times y prime equals 0. And we're solving for y prime. And so, please. Oh, so it's the derivative of 12. Is equal to, so we're taking the derivative of everything there. Thank you for your question. 3x squared y squared times y prime minus 4x e to the y times y prime equals, change all these signs, minus 2xy cubed plus 4e to the y, right? And then we'll factor out the y prime and divide. We're talking about y prime times 3x squared y squared minus 4x e to the y equals minus 2xy cubed plus 4e to the y. Y prime equals minus 2xy cubed plus 4e to the y all over 3x squared y squared minus 4x e to the y. So once you get that whole line again with the derivatives, you move every non-y prime term to the right or the other side of the equal sign, factor out y prime divide. That happens every single time. We were interested in the point negative 3 comma 0. That equals, that 0 is very convenient. That's 4 over 12. 1 over 3. Y minus 0 equals 1/3 times x. Is it plus 3?
Yeah.
Y equals 1/3 x plus 1.
Dr. Wayne.
Yes.
Okay. It seems pretty long.
Oh. So, no. Yeah, that's where we're headed. Yeah, they're going to be long. Yeah. So, yeah, I mean, that's why I was surprised. I said implicit differentiation. Nobody started groaning or anything like that. Yeah, it can be like this. Yeah. So, but this one, I purposely made long because, you know, I want to be able to do all of them, right? So, but if you know how to do this one, then you can do most of the ones that I'm going to ask you to do, right? So, I mean, that one was purposely made long. In general, they won't be as long as this, right? And I do it methodically. Like, I do this, 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 this. When you do this fast, it'll go faster. Like, some people just write it all in one line and just do it. So, finally, we'll just verify y equals 1/3 x plus 1. All right, perfect. Okay. Questions about this? Okay, good. We'll end there. Tonight, I'm going to write the test. We'll come back tomorrow. We'll review for it. Yeah. We're here tomorrow as long as you have questions. So usually review days, we might end early if we get through everything we need to get through. Yes, please.
When are we going to get the test?
So, that should probably be, once I've written it, then I can write the practice test.
Tomorrow we'll go.
Yeah, I mean, I would imagine it should just be put in the homework system. So if you go into the homework system, there'll be a thing that says, here's the PDF for the practice test.
Oh,
Yeah.
I think
Yeah, always.